Hello everyone. In this video, I'm going to go over some homework on the topic of independence. So I've gone ahead and just pasted in here a little bit from the notes how you check for independence of events. If any of these three equations are true, events A and B are independent. And then it's up to you to decide what is A and what is B of your two events. You can assign them either way. The first event can be A, the first event can be B, whatever you like better. So you have these three ways of checking, whichever is most convenient to you. Let's look at the first set of questions. Consider the experiment of drawing a single card from the deck shown below, which has 9 cards. Each card has a shape, triangle, diamond, square, or circle, and a color, black, gray, or white. So here are our cards. Everyone can get equally confused by these cards because no one's ever seen them before, unless you've taken my class. Determine whether the events getting a triangle and getting a white card are independent. Okay, so I'm just going to try the first way of checking this first equation here. So I'm just going to check whether this equation is true. All right, I'm going to try to not use highlighted version. So to check whether an equation is true, you need to calculate both sides and then just see if they're equal or not. So first I'm going to calculate, well, first I need to decide what's A and what's B. So I'm going to check whether the probability of getting a triangle, so that's going to be my A. I'm going to see if that's the same as the probability of getting a triangle given that I have a white card. And I'm going to do this in one card. So when I talk about getting a triangle and a white card, I mean in the same card. So what is the probability of getting a triangle? There's 3 triangle cards and there's 9 total cards. So this is 3 out of 9. Now what's my probability of getting a triangle card if I know that the card is white? If it's given that it has to be a white card. So if I'm able to somehow see the colors and I make sure I grab a white card, what's the probability that it's a triangle? Now that's 1 out of 2. Okay. So these are not the same number, right? 1/3 and 1/2 are different numbers. So this equation is not satisfied. They're not the same number. Okay, the equation is not true. Numbers are unequal. So events are not independent. So knowing that the card is white makes a big difference to the probability of whether it's a triangle. Makes a much higher probability of being a triangle, simply because there's no square or circle in the white card, so it's a higher probability that it's the triangle. Okay, number 2, determine whether getting a diamond and getting a gray card are independent. All right, let's just do this the same way. So I'm going to check probability of getting a diamond, and then I'm going to compare that to probability of getting a diamond if I know that it's gray. Okay, so overall probability of getting a diamond, there's 3 diamonds out of 9 cards. Now what if I know that the card is gray? Now what's the probability that it's a diamond? 1 out of 3. Okay, so actually, in this case, it is independent. This might be the only pair of independent events that you can find with this deck of cards, though, because it's a weird deck, right? These are equal, so the events are independent. So if you know that you have a gray card, that does not affect the probability of whether it is a diamond. It would affect the probability of whether it's a circle, for example. It would make that completely impossible, but it does not affect the probability of whether it's a diamond. Okay. Number 3, determine whether getting a black card and getting a white card are independent. Okay, so this is almost like a trick question because you're doing this in one card. Mutually exclusive events are never going to be independent. If I know that I got a black card, that definitely changes the probability of whether I got a white card because it makes it go to 0. Right? So let me show you. We can check with the equation as well. Probability of getting a black card versus probability of getting a black card given that it's a white card. The probability of getting a black card is 4 out of 9. Now, what's the probability that you get a black card given that it is a white card in the same card? It's not possible, right? There's no white cards that are black cards. Not in this deck of cards. You can invent one that's like that, but this deck of cards does not have it. there's 2 white cards, neither of them is black. So this is 0. So these are not the same number. Not the same. Oops, keep tabbing over to the wrong spot. Not equal, so not independent. Yeah. Okay. Mutually exclusive events will never be independent, by the way. All right. So now let's do something a little more complicated. Let's consider drawing 3 cards in order with replacement. With replacement means we are putting them back in the deck. It's not how we usually draw cards. We usually draw cards to play games with, which means we do not replace them. But let's say that I do put them back in the deck every time before drawing the next one. What is the probability of getting a gray card, then a black card, then a white card, triangle, then a diamond, then a square? Okay, so the reason this is in the same homework with independence is because when you know events are independent, you can just multiply their probabilities together. So if I'm putting the cards back in the deck every time, then the probabilities for each individual card are independent from each other. Okay, so that's the important thing to know here is when drawing with replacement, all events associated with different draws are independent. Okay, so we can calculate if I want the probability of a bunch of events, like A and B and C, and even I could keep going like this. I can just multiply their individual probabilities together like this. And just keep going. As many as you want. Okay. So probability of drawing a gray card, then a black card, then a white card is just going to be probability of gray, probability of black, probability of white. And I'm putting them back every time, so it's going to be like 3 numbers that are out of 3 fractions that are all out of 9, like this. Out of 9. Out of 9. Okay, so probability of drawing a gray card is 3 out of 9. Probability of drawing a black card is 4 out of 9. Oop. And probability of drawing a white card is 2 out of 9. Same deal for triangle, diamond, square, just different numbers. So probability of triangle times probability of diamond times probability of square. The probability of drawing a triangle is 3 out of 9. Probability of drawing a diamond is 3 out of 9. Probability of drawing a square is 2 out of 9. Okay, let's look at one with students. During spring 2023, there were 2,174 students enrolled at SU, and their majors and their years were as shown down here. Consider the event of selecting one student at random. Determine whether the event is undeclared and is a freshman or independent. Now just think about this for a second yourself. If you knew that someone was a freshman, would that change the likelihood that they have an undeclared major? Look at these numbers right here. There's 127 undeclared freshmen, but only 9 sophomores, 1 junior, 0 seniors. So yeah, knowing that they're a freshman, it should make it more likely that they're undeclared, actually. There were almost as many undeclareds as there were business majors. So these are definitely not independent. But we can more formally show that using these equations. So let's just calculate what's the probability the student is undeclared. And then we can compare that to probability that they're undeclared given that they're a freshman. And you can do this in either order. You don't have to do it this way. We could have swapped the words undeclared and freshman in these equations here. Okay, probability of undeclared overall, there's 137 of them, or there were 137. I hope they've declared by now. Out of 2,174 total. Now for the given freshman part, that affects both your top number and your bottom number. On the top, you want to put number of undeclared given they are freshmen. And then on the bottom, you want to put number of just overall students, but still given that they are freshmen. Okay, so you're really only going to be looking at that freshman pool in the bottom. So undeclared given that they are freshmen is 127. And in the bottom, overall students given that they are freshmen is 547. Okay. Are these the same number? 137 out of 2174, 127 out of 547? No, this first one is really small. It's like 1 out of 20. And the second one here is like 1 out of 5, approximately. These are definitely different numbers. I hope you could tell those are different numbers even without putting them into a calculator. It's 3 digits over 4 digits versus 3 digits over 3 digits. Yeah, those are different numbers. Okay, so these events are not independent, not equal, not independent. All right, number 7. Determine whether the event is a business major and is a senior are independent. I'm guessing there's probably nothing independent in this table because people are not like decks of cards where everything is distributed, evenly. So there's probably nothing independent, but it could be close to independent. It's possible that they're close to independent. Um, but actually, now that I'm looking at this, are you guys seeing the same thing that I am? The seniors are actually a little bit light on business majors during this semester. I'm not sure why. 190 versus 218 and 235. They started off, yeah, well, they started off low, but maybe they were a little closer together in the freshmen. All right, let's check this out with the real numbers to figure this out. So probability of business versus probability of business given they're a senior. I'll just always do these the same way if it's possible. So probability of business is, there's 642 of them overall. So if I grab a random SU student, that's the probability from that semester. That's the probability they're a business major. Now the probability that they're a business major, given that they are a senior, so I only want to put business seniors on the top. So number of business given senior. And on the bottom is just number of students given senior. So it's basically all the seniors on the bottom. So business seniors on the top, there's 190 of them. And on the bottom, just all the students, but given that they're a senior, so that's going to be all your seniors. So 643. Okay, now are these the same numbers? Now, this is a little harder for me to see. Let me try putting these in the calculator, and it's actually 642 out of 2174. Okay, so that's 29.5% approximately. And for this one, I think it's not actually that far off. 190 over 6.3. It looks like about 1/3 to me. 190 out of 6.3. Wow, wait a minute, that's really close. Hold on. It's the same to the first decimal place there. It can't be exactly. Let me give a couple more decimal places because this is giving me 29.5% again, but I'm like, they must be off somewhere. So the next digit would be 5. Do this one again. 6, 4. Yeah, they're not off until the third or the fourth decimal place there. Wow, that's really close together. So technically they're not independent, but they're like super close to being independent. Very close to independent, but technically not independent. Okay, so you guys can see like actually there's some wiggle room for what it really is meant by independence. If you're using data from the real world, you'll find almost nothing to be truly independent, but you can have things that are close to independent, which is kind of what we would expect. We wouldn't expect that like your major depends on your year. I mean, that would be kind of strange, other than the whole undercleared thing, which is self-explanatory. All right. These last 3 questions, consider the experiment of selecting 4 random SU students in order with replacement. So again, with replacement is like putting the students back into the pool before we select each one. That is going to make these draws to be independent from each other, which means we can use this probability technique up here, where we just multiply together individual probabilities. So what is the probability of getting a freshman and then a sophomore and then a junior and then a senior? So I'm just going to do probability of a freshman times probability of sophomore times probability of junior times probability of senior. And I can just do these individual probabilities without worrying about any givens because I am drawing with replacement, which makes the events from the different draws independent. Okay, so probability of getting a freshman is 547 out of 2174. 547 out of 2174. Oh, okay. I'm going to go ahead and set up these to all be out of 2174. So I'll just copy paste this like that. Then the probability that I get a sophomore, if I put that first student back, 445 out of 2174. Probability of getting a junior, 539. Probability of getting a senior, 643. And then for these next couple questions, I'm just going to use basically like the same technique. So probability of getting a senior, getting another senior, getting a fourth senior. So I'm just multiplying the same thing together 4 times. It's going to be this number, boop, 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 4 times. You can abbreviate this with an exponent like that if you want. Probability that all 4 are the same year. Now this is significantly trickier. You can't really approach this the same way you do with card problems, where like you take any student and then after that try to match the same year. The reason is because people are not like cards. There's a different number from each year. So if you don't know what year your first student was, you won't know how many students are left to match them, or how many students there are that could match them for the second draw. Actually, what you need to do for this question is a little bit of mental interpretation. Oh, I finally got my blue text down here. I forgot about doing it. All 4 the same year can be interpreted as 4 freshmen or 4 sophomores or 4 juniors, or juniors. I'm sorry, I'm struggling, guys. I'm getting over a cold. I don't know if you can hear that in my voice. It's all nasally. Or 4 seniors. And these 4 outcomes are mutually exclusive, so we can just add up these probabilities. So probability of 4 freshmen plus probability of 4 sophomores plus probability of 4 juniors plus probability of 4 seniors. Okay. And for each of these, well, you saw how to do it for seniors, right? It's basically the same technique for all of them. Like it's going to be something to the 4th, something to the 4th, something to the 4th. And then I already know what the one for the seniors is. It's this one right here. Okay, so the probability of getting 4 freshmen is, just take that freshman probability, 547 out of 2174, multiply it together 4 times, do the same thing for the sophomores, 445, 4, multiply that together 4 times, juniors, 539, multiply that together 4 times, and then since this is an OR event, we add these 4 answers up. Okay, so it looks a little bit complicated, but it's pretty straightforward actually. All right, if you have any questions about any of this, send me an email.